Hello there, Mr. Sutton here, bringing you the Algebra 2 5-2 Part 2 homework solutions on properties of rational exponents and radicals. For this problem, we are adding two terms that both have the same 14 to the 1/4 power, same base and exponent. So we can treat these as essentially like terms. This is kind of like a 3x plus 9x situation. So the answer is just going to be 3 plus 9, or 12 times this common factor here. So 12 times 14 to the 1/4 power. For this problem, we have like radicals being added. We basically have 1 4th root of 10 plus 7 4th root of 10. So 1 plus 7 gives us 8 4th root of 10. For this problem, I'm trying to subtract these radicals. In order to simplify this any further, maybe I could simplify this 5 radical 12 a little bit, because right now I don't have like radicals, so there would be no way to combine these if I just left them the way they were. 12 I can break up into the square root of 4 times the square root of 3. Square root of 4 is 2. 5 times 2 is going to be 10, so 10 radical 3 minus 19 radical 3. And then if I subtract these, 10 minus 19 is negative 9, so we have negative 9 radical 3. To take the 4th root of this expression, I'm first going to split it up, just for my own sanity, into 4th root of 81 and 4th root of y to the 8th. 4th root of 81 is just 3, so that's a perfect 4th power. 4th root of y to the 8th, I have to divide, so we have 8 divided by 4 gives me y squared. Since this is an even exponent, I don't need an absolute value, so 3y squared is my final answer. For this problem, I'm trying to take the 4th root of all this craziness here, so I'm going to split this up. I'm going to have the 4th root of my numerator, k to the 16th, divided by, and I'm going to split up my denominator actually into 4th root of 16 and 4th root of z to the 4th. So I'm doing all of these individually. 4th root of k to the 16th, I'm just doing k to the 16 divided by 4, so that's k to the 4th. So 4th root of 16 is going to be 2. And then 4th root of z to the 4th, I've got 4 divided by 4 is 1. Since it's becoming an odd power, but it used to be an even power, I need to include an absolute value around my z. And then this is as simplified as it's going to get. This expression is considered not fully simplified because we have a fraction inside a radical. So in a moment I'm going to be splitting this up. Before I do though, I'd like to combine these h's a little bit. So since we're dividing, I subtract the exponents, and I'm just going to put the remaining exponent wherever the power was higher. So I basically in the denominator have h to the 7 minus 1, or h to the 6th. And now that I've simplified that, I'm just going to split this up. So the numerator and denominator are both going to get their own 6th root. And when I actually take the 6th root of these variables, I'm just dividing the exponent by the root. So we have g to the 6 divided by 6, or g to the 1, or just g. I'm going to need an absolute value on that g because it was originally an even power. So to simulate the always make it positive sort of effect, I need to force it with an absolute value if we ended up with an odd power. And the same sort of thing is going to happen with this h. I'm going to have absolute value of h, again because I started with an even power and I turned it into an odd power. For this problem, we're just going to reduce this using normal rules of fraction reducing and some exponent rules. So let's start with the 18 and the 27. Those can be reduced by 9 to give me 2 over 3. Let's do the w's next. I'm going to subtract the exponents and put the exponent wherever the higher exponent was. So since we're higher in the denominator, I'm going to do w to the 4/3 minus 1/3 down there, which is just w to the 3/3, or just simply w. And then I have a higher exponent in the numerator for these v's. So in the numerator, I'm doing v to the 5/4 minus 1/2. 1/2 is really the same as 2/4. 5/4 minus 2/4 gives us 3/4, so v to the 3/4. To start simplifying this problem, eventually I'm going to need to make sure there's no perfect cube factors inside here. But let me first start by splitting all this up. So I'm going to give the 125, the r's, the s's, and the t's each their own personal cube root, like so. Alright, now let me go piece by piece, and if it's a perfect cube, I will just take the cube root. Otherwise, I will split it up into a perfect cube times something else. 125 is a perfect cube. That's 5 to the third. So that's just going to be 5 if I take that cube root. For the next one here, so when we're dealing with variable exponents, any exponent that's a multiple of 3, because that's the index here, is going to count as a perfect cube. So r to the fourth is not a perfect cube, but I can split it up into r cubed times r. R cubed is the biggest cube that's less than r to the fourth. For this next one, s to the ninth, well, I can just do 9 divided by 3 right off the bat. So that's just going to be s cubed, nothing special that needs to happen there. And then for this next one, 7 is not divisible by 3. The highest multiple of 3 that's less than 7 is 6. So I can split this up into t to the 6th cube root of that times the cube root of t. Going back through now, I've got a 5. Cube root of r cubed is just r, so 5r. Let's see, s cubed is along for the ride. And then we have the cube root of t to the 6th. 6 divided by 3 gives me 2, so t squared. And then for my radicals, I have a cube root of r and a cube root of t that are left over, so that gives me a cube root of rt. In order to simplify this, I'm going to have to take care of this radical in the denominator, and I'm going to do that by multiplying by something that's going to give me a perfect, let's see, my index is 4, so I need a perfect fourth power inside this fourth root. So the next highest fourth power after d to the 7th is going to be d to the 8, because 8 is divisible by 4. So if I multiply this by the fourth root of d over the fourth root of d, that gives me a c cubed fourth root of d upstairs and fourth root of d to the 8th downstairs. Fourth root of d to the 8 is just going to be d squared, so we've got this stuff up here over d squared. This problem is going to take a little bit of work here. One of my issues is that I have a fraction inside a radical, so I'm going to have to split that up. While I'm splitting things up, I'm also going to split up the 160 and the m to the 6th. So 160, m to the 6th, n to the 7, they're all going to get their own personal fifth root. Lucky them. Alright, so another issue I have, not even thinking about perfect fifth powers that might be inside things up here, I have a radical in the denominator, and I can't get rid of it by merging things and canceling stuff out. So I need to multiply by something that will give me a perfect fifth power in this fifth root downstairs. The lowest fifth power that's higher than n to the 7th is going to be n to the next multiple of 5, so that's going to be n to the 10th. To get n to the 10th down here, I would need to multiply by the fifth root of n cubed over the fifth root of n cubed. I have to do the same on the top and bottom because this is really just multiplying by 1, believe it or not. So now that I've done this, I'm going to split things up a little bit. And then after I split things up appropriately, I'll do all the fifth rooting that I need to do. So let's take a look at fifth root of 160. Are there any perfect fifth powers that go into 160? Well, the first fifth power that I can think of is 2 to the 5th, which is 32. That goes into 160 5 times, so I can break this up into fifth root of 32 times fifth root of 5. Next up, we have the fifth root of m to the 6th. Since the exponent is higher than the index, that means that we can split this up. So I'm going to break this into m to the fifth root of that, times the fifth root of m. And then since the 3 in here is lower than the index, we can't split this up at all. It's already as good as it's going to get, so we'll just leave that there. However, the denominator now, the whole point of multiplying by this was to get n to the 10th inside that fifth root. Alright, so we've done a lot of work to get here. Going through now and taking some fifth roots. Fifth root of 32 is 2. Fifth root of m to the 5th is going to be just m. And What else is up here? We still have a fifth root of 5, an m, and an n cubed that can all move in together inside one big fifth root. So 5m and n cubed. And down here, the fifth root of n to the 10th, 10 divided by 5, that's going to give us an n squared. And that is as good as it gets. For this problem, the first of two problems in the honor set, we have the same radicals being added together, so we can just add the coefficients and keep the radical the same. 12 plus 9 is 21, so 21 times the cube root of y is our answer for this one. For this problem, I'm trying to subtract these radicals. Now, right now I don't have any like terms. I have the same type of radical. These are both cube roots, so I might be able to combine these, but I'm going to have to simplify each of these individually first and then see if there's anything I can actually work with. So let's start with this first one here. 32, does 32 have any perfect cubes that go into it? Well, 8 is a perfect cube, and that goes into 32. So I can split the 32 up into a cube root of 8 times cube root of 4. So that's my first split. The biggest perfect cube that goes into p to the 10th is the biggest multiple of 3 for the exponent. So that'll be p to the 9th times p, both of those in cube roots. Moving over to this other expression, I can't really do anything with the 4, but I can split up my p to the 4th into a cube root of p to the 3rd times cube root of p. Everything else here, the 9, the p squared, cube root of 4 is going to have to stay the same. Simplifying a little bit now, cube root of 8 is 2. Cube root of not p to the 9th, dividing there, we get p to the 3rd. And then I have the cube root of 4p left over for the radical. Moving over here, the only thing I can do is take the cube root of this p cubed, which is just p. But now, since there's already a p squared out here, p squared times the p that comes out of this radical here is going to be a p cubed. So we have minus 9p cubed. And then what else is left? We have a cube root of 4, cube root of p. Those go together in that radical. So taking a look at the big picture, we have 2p cubed, cube root of 4p, and we have a minus 9p cubed, cube root of 4p. So everything is the same except for the 2 and the negative 9. So these are like terms, crazy like terms, but they are like terms. So we can actually subtract these. 2 minus 9 is negative 7, so we have negative 7p cubed, cube root of 4p.